Okay, so we are going to start the reflections, the first set for the unit on correlation and linear regression. And of course, we'll have some problems in here that also go back to prior units. So identify the explanatory variable and response variable for this relationship, the weight in kilograms and the height in centimeters of a person. So in this unit, we are dealing with two quantitative variables. And in theory, one might explain the other. So weight and height are the two variables. Gaining height naturally adds to your weight. Sadly, as an adult, you cannot grow taller just by gaining weight. Darn. All right, so height explains the weight. Weight doesn't explain the height. So there's your, the answer choice here is A, the explanatory variable is height, and the response variable is weight. Now problems 2 through 4. Often the percent of an animal species in the wild that breed again is lower following a successful breeding season. This is part of nature's self-regulation, tending to keep population size stable. A study of merlins, small falcons in northern Sweden, observed the number of breeding pairs in an isolated area and the percent of males banded for identification who returned the next breeding season. So here are the data for the 9 years. There are the number of breeding pairs and the percent of males returning. So they told you in the problem that with more breeding pairs, we expect less males returning. So the number of breeding pairs explains the response of the percent of males returning. So percent of males is the response variable. Then it asks us, which of the following does not correctly describe the scatter plot? So they're talking about direction. So you might recognize Duff's here: direction, unusual features, form, and strength. So I'm going to go ahead and first use a Statlet to graph the data. So if you don't have access to a calculator, at least you can use Statlet. You go to statlet.com and you look for two quantitative variables. In this case, our variables are breeding pairs and percent of males returning. So I'll go ahead and click that. Type in breeding pairs. And then you can just put in the spaces with or without commas between the values. So very easy to enter here. And then you hit begin analysis. And there is your scatter plot. Now you can actually go ahead and calculate correlation, which is R, and you can even calculate a least squares regression line. When you do hit that button, so this is our scatter plot, right? And then here is the residuals. I haven't taught you about that yet. And this is a dot plot of residuals. And we'll talk about that later when we talk about checking if something's appropriate for linear regression. Not today's lesson. So you can see here that the dots, they're pretty closely scattered. This is a moderate. It's definitely not a weak. And if you use the value of R to set, oh, which one is it? It's actually almost all the way to strong. Typically anything with an absolute value of 0.5 to 0.8 is considered moderate. 0.8 to 1 is considered strong. So this is just under strong. This is, I would call it a strong moderate or just a moderate. Okay. Okay, to create a scatter plot on the TI, you're first going to have to go ahead and enter the data. So you hit stat, that button right there that's red right now. Then you're going to hit enter. We just want to be in edit. So you can hit 1 or you can hit enter. And you have list 1 and list 2. Now, if you want to, you can actually go change those names, but let's keep it simple for right now. And I'm going to put the breeding pairs in list 1. Oops, I don't need that many 38s. All right, so there we go. And then in list 2, oops. And you should have the same number. You can also tell how many data points you've entered. I know we're doing 9 years, and you can see right here, it's going to enter the 10th year, but I don't have a 10th year. And if I go up one here, it says the 9th data point is 38. So let's assume I've entered these data points correctly. Now you're going to, since we want to see a scatter plot, we're going to graph, and you see that little blue on the top. It's going to be under the screen on the calculator. It's called stat plot. So hit second stat plot, and we're going to hit 1. We're going to just need the first graph. Now notice all the graphs are off except for 5, which says plots on. So I believe 4 turns all the plots off. I think 5 turns all the plots on. So let me go ahead and go back. I'm not sure what it does. All right, and I'm going to hit 4 just in case I did something. Oh, I guess if it's entered. Oh, I didn't like that. All right, so stat plot. Actually, I'm going to play with it. 5 plots on, second stat plot. Yeah, you can see all the plots are on, but I don't want the plots on, so I'm going to hit plots off. And there we go. So you don't have to play with those two, but I thought we'd play with them since I had you here with me. So we're going to go ahead and go to plot 1. First thing we have to do is turn it on, or it won't plot. And then you come to the next one, which shows the type. So we want a scatter plot, which is actually that first one. It's probably hard to tell. This is a line plot, so it would connect dots there. This is a histogram, and then you remember box plots. You can do those on your TI-84 as well. And this, I'm not quite sure what type that one is. I'd have to go look. So X list is list 1, Y list is list 2. That's very normal. And then once you've got this all set up, you can hit graph. And then normally, it's not zoomed to the right level. So you're going to hit zoom, and you see a whole bunch of choices here. See the one? We're in stats class. I always remember it's 9. And there is my plot. There's my plot. Okay, so that's how you can get the scatter plot to look at it. Now you'll notice I don't have an R here. And regression is technically the next one, but let me show you something, and I'll do it again when I do the next set of reflection solutions. You can actually go to Stat, Calc, and then it's LinReg. Either see number 4 there. You can do 4 or 8. It doesn't matter. The only difference is it says, oh, A is the coefficient of X. Here, B is the coefficient of X. Frequently, you're going to find that when you look at stuff, they tend to do that one. Doesn't really matter. Okay. Frequency list, we almost never have. That's only if you have multiple data points at the same, multiple dots, the same values. And we'll hit calculate, and it will actually give you the equation, which should match what we had on our statlet. Okay. In fact, I'm going to go, let me check that real quick. What was it? Yeah, roughly. That was roughly what it was, so I looked it up from the statlet. Now you'll notice there's no R. So the way you get your correlation coefficient is you go second catalog, and then you got to go turn on, don't ask. Now you can hit D here. Where is D? I'm just going to scroll. You look for diagnostics on. So you see that? I don't know why you have to do this on the TI-84, but you do. So we're going to go back and calculate it again. Doesn't matter which one, by the way, so I'll just do this one since it's faster. And now you see there's the R, and that's the same R we had before. That is a correlation coefficient for a moderate strength in the negative direction. Okay, so since we have our scatter plot, which of the following does not describe the scatter plot? The direction is decreasing, so A is okay. We don't see any unusual features, so B is okay. The form is linear. It's fairly linear. And then the strength we already know is almost strong. It's on the strong side of moderate. And so the strength is definitely not weak. So the one that is does not correctly describe the scatter plot is D. Now, you go ahead and calculate the correlation for a linear model. Which of the following correctly describes the correlation? I just showed you how to get that, and this is the screen we pulled from. Again, it would be stat, and then you go calc once you have your data in the list. So you can see here it's negative 0.794, which is almost strong, not quite. It's actually moderate. So be careful, don't miss the negative. It's very easy to miss on a calculator especially. I don't know what it is, but it's such a tiny little sign there. So the correct answer is D. Number 5, the weight gain of corals in aquariums where the water temperature is controlled at different levels. Identify the explanatory variable and the response variable for this relationship if possible. So you don't expect the weight gain to affect the temperature, but adjusting the temperature probably affects the weight gain. So the temperature is the explanatory variable and the weight gain is the response variable. Number 6, the scatter plot shows the relationship between height in inches and weight in pounds for the members of the U.S. 2016 Olympic track and field team. Describe the relationship between height and weight for these athletes. So I'm going to practice again. Let's do the DUFs. So direction is positive. There are no unusual features. The form is linear and the strength is moderate. So there's a moderately strong positive linear relationship between height and weight for these athletes. There are a few athletes that weigh much more than other athletes, so you can see the high weights up here with their same height. So then they they take the graph and they go, oh, but these are two different types of athletes. The ones who do shot put, discus throw, and hammers, and then those who do track and field. And you could probably guess which ones do you think do the shot put, discus throw, and hammer? The heavier ones. So they've highlighted these athletes in blue, all right? So how is the relationships? Well, we can see the weights are higher for the blue dots for a given height than the black dots for a given height. So we say the relationship is the same in the sense for both groups of athletes. There is a moderately strong positive linear association between height and weight. What's different is athletes who participate in the shot put, discus throw, and hammer throw tend to weigh more than other track and field athletes. So here, so they basically highlighted these are your shot put. I'm saying putt instead of put. There we go. Okay, number 8. So we're going to review a little bit on randomly sampling using a simple random sample, so to speak. And we wish to draw a random sample without replacement from a population of 50 households. Suppose the households are numbered 0, 1, 0, 2 up to 50, and suppose that the relevant line of the random number table is this. So how could we use this to pick some households? Here you can see they picked 5. It wasn't obvious up here that we're getting 5, but we'll just keep picking until we get at least 5. So we need 50 total outcomes, which means we're going to just use 2 digits at a time. So I'm going to just go ahead and separate these out into 2 digits. So we have 1136. We don't drop the 2 just because it looks like it's alone. We put it with the 3. So we have 23, 56, 92, 96, 23, 79, 8, 42, 46, and 84, and I'll stop there. Now, we need to also know which ones do we want. Do we use all of these? Is it just 11, 36, 23, 56, and 92, like choice D? Well, we can't really have household 56 if there are only 50 households. And there is no 0, 0 because we started numbering at 0, 1. So we're going to ignore everything that's higher than 50 as well as 0, 0. And we should not be sampling the same household twice. So you can see there are 2 23s there. So we ignore repeats as well. So ignore 0, 0 and 51 through 99 and repeats. So if I cross out 11, 36, 23, that's all good. 56 is too high, so it's 92, 96. 23 is a repeat. 79 is too high, so the next one I pick is 0, 8, and then finally 42. So the correct answer is C on this one. Number 9. A public opinion poll in Ohio wants to determine if registered voters in the state approve of a measure to ban smoking in all public areas. They select a simple random sample of 50 registered voters from each county in the state and ask whether they approve or disapprove of the measure. So what is this an example of? You're probably tempted to say, hey, it says simple random sample. It looks like a simple random sample, except they're doing one for each county. So each county is its own sample. What does that look like? Oh, that looks like the way we draw a stratified random sample. A stratified random sample is just a bunch of simple random samples from every group. So there you go. It is a stratified random sample, since they're taking a sample from each county in the state. A marine biologist wants to estimate the mean size of the barnacle Semibalanus balanoides, I think, on a stretch of a rocky shoreline. To do so, he randomly selected 20 10 by 10 square inch plots and measured the size of every barnacle in each plot. What is this an example of? Well, he's randomly selecting entire groups or clusters, all right? And then he's surveying everyone in that particular group. Hopefully that reminds you of a cluster sample. See, well, we'll do this whole group or that whole group and that whole group, but we don't do all the other clusters. So that is called cluster sampling. Number 11, if changes in a response variable are due to the effects of the explanatory variable as well as effects from another variable, and we cannot distinguish between these effects, we are said to have what? So a cause and effect relationship has nothing to do with it. It would be, that's only for random assignment in an experiment. Placebo effect, this has nothing to do with placebos. Correlation, actually, you don't need a two quantitative variables for this, and correlation is for two quantitative variables. You can have this effect also when you have categorical variables. It is confounding. So the other variable is confounding our results. Extrapolated is another thing where you go beyond the range of your data. That has nothing to do with this situation. So it may be true, the true reason both variables are changing, and time itself is a frequent confounding variable. Number 12, 80 volunteers who currently use a certain brand of over-the-counter allergy medication have been recruited to participate in a trial of a new allergy medication. The volunteers are randomly assigned to one of two groups. So we got random assignment, and they are volunteers. So one group continues to take their current medication. The other group switches to the new experimental medication. Each is asked after 2 weeks if their allergy symptoms are worse, better, or about the same as they were at the start of the study. Which of the following best describes a conclusion that can be drawn from this study? So conclusion, we got to think about who we are in the study. Well, it is volunteers. So we can only talk about people in the study, all right? Or people very similar to people in the study. You might see that as well. Now, we do have random assignment of treatments, so we can say causes. Now, in this particular case, you can see both of these say reduces A and B. And this says for anyone who suffers allergies, so A is out. This one is for people, for the subjects in the study. And we're going to go ahead and stick with that. The other one says we can determine, prove more with a new drug, but we can't establish cause and effect. We did random assignment, so we can. And we can still draw conclusions because we're just comparing the two drugs. You don't always have to have a control group. You just have to be comparing. Control groups are nice, don't get me wrong. But sometimes you are going to give them medication. Just why make them suffer through allergies if you know it helps anyways? Yeah, see, it said there was no control group. There was no control group, but that's fine. We can still draw conclusions on this one. Okay, number 13, probably the one that's going to give you the most trouble on this assignment. It looks super simple. I was looking at it, I was like, normal distribution, so easy. Well, let's do it. The SAT math scores for applicants to a particular engineering school are normally distributed with a mean of 680 and a standard deviation of 35. It's a normal distribution with a mean of 680 and SD of 35. Suppose that only applicants with scores above 700 are considered for admission. What percentage of the applicants considered have scores below 750? So this is a conditional probability. We have to look at the probability that someone has scored less than 750 given they scored at least 700. So we're going to need a couple things. We're going to need the probability of X is greater than 700. That's our given. As well as the probability that X is greater than 700, but also less than 750, which means it's between 700 and 750. So let's start with the first part, it's greater than 700. And if I do this on the calculator, don't worry, I'll show you in a sec. It would be the normal CDF. My lower boundary is 700, the upper is infinity, and the mean is 680, and the SD is 35. Now, the reason I love the staplet is it gives you a beautiful figure. It's a pretty picture right here. And you can clearly see that we are going to the right, right? Because we're saying greater than 700. So make sure here, hopefully it's obvious, but it may not be. It's easy to get mixed up. It's always nice to draw this whether you're using staplet or not. It does not have to be to this detail. Just tell me where the X is and highlight the area of interest, and that's the main thing, okay? So you can see that since it's to the right of the mean, it's definitely less than 50%, but it's not trivial. It's pretty big. And in fact, if we, from the staplet, you can see it's 0.2839. Now let's go ahead and practice doing this on the calculator too, because I'm not, there'll be a time I won't let you use the staplet, okay? So how do we do it? Here you go. All right, to find the area in a normal distribution, you're going to hit second distribution on the calculator. And you see normal CDF. We never use normal PDF in this class. We always use normal CDF. And in this case, our lower is 700 and our upper is infinity. So I'm going to go 1, and you see the little EE there, second EE, and then you just put 99. That's as close as we get to infinity on this calculator. Then I can, since I'm putting it in the actual X values, I can go ahead and put in the actual mean, which is 680, and then the actual standard deviation, which is 35, and then paste. And you see I get 0.239 roughly. Okay, so we had 0.2839. Okay, now you're probably going, hey, the answer is B. No. Remember, we're doing a conditional probability, all right? Oh, by the way, on the staplet, the nice part is it does give you the z-score, but if you're drawing this, hopefully you realize since the standard deviation is 35, it's less than a standard deviation above the mean. And that's a good way to draw this. So you should have a rough idea where these values are relative to the mean. So now we're going to do the other probability between 700 and 750. So we're going to go from here to 2 standard deviations above the mean. So I know the z-score for that one is 2. But we're just going to do actual values. So we're looking for this from 700 to 750. All right, and I'm going to find on the staplet it says 0.2611. All right, before I move to the other part though, remember that why am I looking at both of these areas again? Well, we know it's given we're in here, and we know what's the probability of being in here. Well, you can see it's a pretty high probability. It's definitely not A or B, because this is more than half, and I'd say it's more than 75% of the area. I'd say it's either D or E. We're going to have to do some math, but before we do that, let's go ahead and practice doing this one on the calculator. Now we're going to calculate the area from 700 to 750 on the TI-84, second distribution, normal CDF. This time my lower is still 700, but my upper is only 750. Oops, I did that on the wrong one. Here, delete. Let me go back. Change that to 700. There we go. And now this is 750. All right, and then mean and standard deviation don't change. Hit enter, and we get a value of 0.2611, which matches what we got on the staplet. Okay, so now we have both those values, and we're going to bring in our conditional probability formula. Probability of A given B equals probability of A and B over the probability of B. So the probability of A and B is the probability that it's less than 750 and greater than 700. I can actually reword that so that it says, oh, that means it's between 700 and 750, right? That's the value there. And so what's the probability over the probability that it's greater than 700, that they're an applicant who's considered? We know these values now, so we just go ahead and put them in. Hint, if you get an answer bigger than 1 here, odds are you made an error because we don't have probabilities greater than 1. So make sure, it might be tempting to go 0.2839 over 0.2611, but in reality, it is much easier to just go ahead and make sure that this is always less than 1, or at least not greater than 1. Okay, number 14. Suppose x and y are random variables with the mean of x is 38, the standard deviation of x is 12, the mean of y is 35, and the standard deviation of y is 9. All right, realizing it probably helps when I have the laser pointer too. All right, so given that x and y are independent, what is the standard deviation for the random variable x minus y? So we need to know their independence so that we can go ahead and use what we know about combining variables. So combining variables, first of all, we know z is x minus y. We know the standard deviation of x, the standard deviation of y. And so I created this variable called z. So it's a combination of x minus y, and we're looking for the standard deviation of this new combined variable. Since we are combining variables, we must use variance. So I'm going to write variance of z is the same thing as variance of x minus y. Now I can break these apart, but remember, when we break them apart, we don't bring that minus sign out. We just change it to the plus of both of them. So variance of x plus variance of y. Variance is never negative. That's part of the reason you don't see a minus sign there. Variance is a measure of spread. So you can never be negative spread. Okay, variance is also the square of standard deviation. So this is going to be 12 squared, and that's going to be 9 squared. All right, and then when I square them and add them up, we get 225. So my standard deviation going backwards is the square root of the variance. Make sure you have this memorized. This is not on your cheat sheet or your formula chart. You probably should write it on your cheat sheet and memorize it by the time you take your AP exam. So we're going to take the square root of this 225, which gives us 15. So our answer is 15. Okay, problem 15, the last one in this exercise, looking at probability models. Which of the following is not a valid discrete probability distribution for the set x1, x2, and x3? So mainly, the main thing I have to check, is the sum 1 and are all between 0 and 1 inclusive? Well, A is valid because these add up to 1, and nobody's less than 0 or bigger than 1. We're fine. How about B? Yep, that one's valid too. These all add up to 1, and everybody's kind of normal. Same thing for C. All those add up to 1. And then you could go, well, D, all of them do add up to 1, but the problem is not all are between 0 and 1. This is a negative probability, so D is the naughty probability distribution function.